Let's see conjugate pairs, conjugate acid-base pairs. When hydrogen cyanide reacts with water, it reacts partially, right? It's an equilibrium, and it will result in hydronium, H3O plus, and cyanide, CN minus. Here what happens, water takes the proton from the hydrocyanic acid, and it forms a hydronium, H3O plus, and releases a cyanide, right? The water and hydronium, there's a relationship. Let's take a look at that. So we can say hydrocyanic is the acid and the water is the base in this reaction, and forming conjugate acids and conjugate bases. So the water become hydronium, making its conjugate acid, right? It should be conjugate acid. Now hydrocyanic acid, let's correct conjugate acid. Water becomes hydronium, conjugate acid, and the hydrocyanic acid becomes cyanide, forming its conjugate base, right? So acid becomes conjugate base and the base becomes conjugate acid. So the pair here, HCN/CN, is the acid conjugate base pair, and then the water, hydronium, is the other base conjugate acid pair, right? This should be base conjugate acid pair, right? And so those are the pairs. The difference between the conjugate pairs are one proton. So make sure you understand that. So the HCN to CN minus is one proton difference, right? Now let's look at amphiprotics. So that's a different term, the unique species, right? Remember amphibians? They live in the water and land, right? So that means simply amphiprotic means, let's take water and it can make hydroxides, and also it can make hydronium, right? Depending on what's in the water. So you can give and take protons for each of the water molecules, different water molecules, right? That's the nature of amphiprotics. Now, if you lose a proton from the water, it'll make a hydroxide, or gain a proton, it'll make water, right? So therefore, hydronium and the water is a conjugate pair, and water and the hydroxide is another conjugate pair. So